Hello, everyone, and thank you so much for joining us today. My name is Samantha Kilgore, and I'll be your host for this NASA Technology Transfer Program webinar on the Microscale Electrohydrodynamic, EHD for short, modular cartridge pump technology. It's my pleasure to introduce our presenter for today, Mr. Jeffrey Didion. Jeffrey Didion is a senior thermal technologist at NASA's Goddard Space Flight Center. Mr. Didion has been the lead investigator and principal engineer for 2 International Space Station, ISS, flight experiments and technology demonstrations, 3 variable gravity experiment campaigns, and 2 suborbital technology demonstrations. Currently, Mr. Didion is the co-investigator and lead experiment hardware development engineer for the ISS experiment, electrically driven liquid thin film flow boiling in the absence of gravity. This experiment is the seminal work applying electric fields to manage two-phase fluid flow and enhance heat transport and microgravity. The results will provide critical data validating advanced thermal management hardware, enabling the next generation NASA science instruments and high temperature, high heat flux applications. Mr. Didion's latest technology initiative investigates NASA's applications for oscillating heat pipes. He has been a NASA collaborator for 4 NASA Technology Research Fellows, as well as a collaborator for the 2019 Space Technology Research Grant Early Career Faculty Award. Immediately following Mr. Didion's presentation on the EHD technology, Goddard's Senior Technology Manager, Joshua Levine, will provide an overview on how to license NASA technology. Before we get started, a few short notes. Your microphone will be muted throughout this presentation. If you do have questions, please type them into the chat box and we will answer them during the Q&A session. So at this point, I'm going to turn it over to you, Mr. Didion.
Okay, thank you for that kind introduction. As Sam said, I'm Jeff Didion from Goddard Space Flight Center. I work in the thermal engineering branch, and today I don't want to leave anybody with the impression this is a one-man show. So I am speaking on behalf of Mario Martins, Matt Showalter, and Frank Robinson as well. We were the team that developed the EHD microscale modular cartridge pump. And we'll hear a little bit about that story and where it came from and why we worked on that. And then we'll talk a little bit about some technology breakthroughs we've made since then using electrohydrodynamics to manage two-phase flow and enhance two-phase heat transfer. The thin film flow boiling work is very exciting to us. So Sean, if you could click to the next chart, we'll get started with the meat of the program here. The EHD cartridge pump was actually came from a need from our colleagues at the U.S. Air Force Space Vehicles Directorate. They were looking for structural thermal plates. In other words, a plate that had some thermal management capacity. And as we'll see, EHDs it's a perfect application for EHD. They also can be applied to electronic structures and enclosures and electronics boards. And in the future, we think there's some work for some application for this in such things as NEP radiators and other high heat flux and heat transport applications. Most dramatically, of course, would be wide bandgap communications. And we'll talk about a concept we have for that a little later as well. Next slide, please, Sean. So electrohydrodynamics is nothing more than applying an electric field to a dielectric fluid. And basically, it's nothing more than that. And it's applicable from nanoscale to macro scale. When you do make this application of electric field, an asymmetric electric field to a dielectric fluid, you get an EHD force represented by F sub E here on the left. And then there are 3 components. The first component on the right-hand side is the Coulomb force or the electrophoretic force, and we use that to pump liquids, and we'll talk about that. The second term is the dielectrophoretic force, and we use that to separate liquid and vapor. And then the third force is an electrorestriction force, which applies only to incompressible fluids. So that's not something we've taken advantage of at this time. EHD is nothing more than applying a voltage. So it's a simple design. It's lightweight. There are no mechanical parts, no rotating machinery. You can control the performance. It's a simple feedback loop. The power consumption is quite low. There's no acoustic noise. And of course, as an electric system, it can be adapted to a smart system. The low power consumption is probably best exemplified by the fact that we can move about 100 times the heat, acquire and move about 100 times the heat that it costs us. So in other words, up to 1,000 times for every milliwatt of power we put into an EHD system, we can move about a watt of acquire and move about a watt of heat. So it's pretty good, even though the actual thermodynamic efficiency of an EHD system isn't all that great. The power consumption is so low, we just really have a hard time carrying. Next slide, please. So the first breakthrough was to get to a micro-scale modular cartridge pump. And this is the pump, the design we came up with. The initial EHD design and a lot of the theoretical work is done by our partners at Worcester Polytechnic Institute. And then we take these thoughts and these designs and make them into hardware. So what you see here is a cartridge pump. It's a manifold of 5 pumps to overcome low flow and also demonstrate the fact that we could pick up heat in different locations. The pump sits in basically a bathtub, and it consists of 2 stainless steel electrodes. Each of these have 10 stages, and then we have Ultem spacers in between the electrodes. So the spacing between the electrodes is the key fact and the key phenomena that we're looking for here. And then inlet and outlet manifolds. And then there's stainless steel cover plates. Next slide, please, Son. So the way the system works, it's a coolant pump. So we're pumping liquid in this case. And what you see here at the bottom in the green is the direction of the flow, and then the characteristic dimensions that we're looking for. So L1 is the ground electrode, or the relative negative electrode. L2 is the distance between the ground electrode and the positively charged electrode. L3 is the distance between the 2 electrodes. L2 is the distance, the length of the width of the positively charged electrode, and on L4 is the distance between one electrode pair and the next electrode pair. That is, all these dimensions are important. L1 and L2 give you the asymmetry, so you can develop the flow. L3 is, of course, you need to be the distance between the 2 pumps, or the 2 positive and negative electrodes. And then L4 is a characteristic length to keep one stage from affecting the other. Now, when you apply the electric field to a dielectric fluid, the impurities in the fluid actually are ionic, and they break down into positive and negative ions, and they are attracted to the oppositely charged electrode, and that's how you generate the flow. So it's very geometric based. The less asymmetry, the lower pressure head, and in the case of these EHD pumps at microscale, it's probably the most difficult case. So that's why we went to the manifold pump system. Next one, Sean. So what can the pump do? Basically, you have in the configuration which we developed it, you have, again, an arbitrary number of manifolds, in our case 5, but in the case here we have 3. You can increase the flow in any given channel to pick up heat or handle a temporary hotspot, or as we show on the right in example 2, you can overcome flow maldistribution. So that's just reality. No matter how well you design any manifold, the pressure drop across the manifold is not going to be uniform, and one channel will get starved relative to another channel. However, with an EHD system, you just up the voltage and you can correct for that. So if we move on to the next chart, please. And this is all for single phase flow. So a little bit of the history. I think the picture on the left is not what I was hoping for. That's a larger scale EHD pump that's probably 20 years old. obviously the picture just isn't what I hoped it would be. Basically, it is a number of tubes inside a larger tube that's about 1/10 of a centimeter in diameter. We move down to the micro scale, basically about 100 micron length or hundreds of microns of length and characteristic dimension. That is the dimension between the two stages, the positive and negative electrodes. But this is about 100 pieces you see in the middle here. You see the 4 component pieces, and then when you add in the Teflon and the spacers and the various electrical bus pieces, you're up to about 100 pieces. The big advance that we made is we dropped this down to about 10 pieces. And you see that on the right-hand side. And these are the actual pumps that flew on STP-H5. Next slide, please, Sean. Thank you. Little publicity for STP-H5. The left-hand picture, if you look up near the top left corner, you would see an arrow that points to the ISOM experiment package. The ISOM experiment package was led by Tom Flatley, who has since retired from NASA, and it consisted of 4 components. The SpaceCube Mini, that's a processor that Tom and his group developed. The CSP, which is another processor developed by Tom's group. The FPS was a Fabry-Perot experiment. I think Bill Heaps, if I'm not mistaken, was the PI on that, and the EHD experiment. We were in we called it a bunker. It was about a 50-pound payload, and we had the 4 experiments that were launched aboard a DoD payload called STP-H5. STP is Space Technology Program. Excellent program. I would recommend working with those people as much as you possibly can. The next slide, please. So this is the STP-H5 hardware. What you see here on the left-hand side is a prototype microscale EHD cartridge pump. You see the 5 pumps that we put in there. And you see on the top, it flows from top to bottom. And then on the right-hand side, you see the STP-H5 experiment package. It was pretty Spartan. We had 8 data channels, 1 voltage. We were allowed to apply 1,000 volts, and we had 1 heater channel. So that would allow us to keep the 2-phase reservoir, maintain the temperature there, and apply heat to the 2-phase reservoir. The working fluid in this case was HFE 7000, which is just a typical refrigerant used for electronics applications. If we go on to the next slide, please. So these are some of the results. I apologize for the eye chart if they are in fact an eye chart. This is just some early data that we took that demonstrates a couple of important aspects of EHD flow. First of all, I think this is over about 3 hours, but the experiment went on for a couple of years. We have mass flow rate and volumetric flow rate, so you see that we can basically go ahead and maintain a given flow rate. In this case, it was 1,000 volts was the power. I think the green is the mass flow rate, so we were flowing at about 0.3 grams per second. And then the blue is a volumetric flow rate, so that's milliliters per second. And then the right-hand side, we just show that we demonstrated thermal control. These are the temperatures on the inlet and outlet, and we just simply did an m.c sub PDT calculation to calculate our voltage, or I'm sorry, our mass flow rate. And then, of course, we used density and converted that to a volumetric flow rate. The red lines are the controller for the 2-phase reservoir. So you see we had about a 3-degree bandwidth on that. So if we move on to the next chart. So the modular pump allowed us, we were able to actually validate it long-term in space. The STP-H5 experiment went for 2 years. We showed that we can, in fact, run one of these pumps long-term. We applied it to a real application that our friends at the Air Force were interested in. We improved the size, weight, and power consumption of such applications. And we also demonstrated, or we can show that, EHD phenomena works at, again, nanoscale all the way up to, regular micro or macro scale. these can be applied to arbitrary structures, and it does work better at higher or at higher scales. So, you know, a 1 centimeter characteristic dimension would leave you with a higher flow rate than something a couple hundred microns. That is, we can get up to about 2 psi, I think we generated in the past. So if you did that and you did two-phase, you'd be a couple hundred watts right there for thermal management. The EHD modular pump was in fact patented. I won't quote the number, and the patent was issued to the 4 authors. Move on to the next one. So we didn't stop there. We went then to the second term of the EHD force, and that's the DEP force. And this is another expression of the DEP force. And what you see on the right-hand side is a huge temperature drop occurring right now. And you see the bubbles that pull off of the grate that you see that looks like a sewer grate, where you saw the bubbles come and go. Sean, if you could play that again, that would be helpful. That's pulling the bubbles off the surface. So that actually allows us to enhance the heat transfer, but it also, in microgravity, makes thin film boiling feasible, because the vapor bubbles will not depart the surface on their own without an external force in the absence of gravity. What you see then here on the graph is a drop in temperature, which represents when you see the bubbles develop, we turn the EHD pump or the DEP pump on, and that represents a greater heat transfer rate or a greater heat transfer coefficient. So the drop in temperature is we're still moving the same amount of heat for a lower temperature difference. And then, you know, the great thing about EHD is it kind of sells itself. You see what goes on here, and then right about now we turn off the DEP, and you see we go back to just regular thin film boiling. Okay, that was laboratory work. Sean, if we can go to the next chart. So what we are seeking to do, and we have an experiment which we will in fact do this in a different configuration, is to combine the modular EHD pump and the dielectrophoretic force to give us some sort of high swap or better swap figure of merit. With the applications, of course, we would hope to be up to micro G up to 10 G. We've calculated the DEP force can be applied at about 10 G. We have to prove that, of course. Electronics components and high power electronics would be a perfect application. Again, wide bandgap communications and high performance computing. Now, if we were to apply it to electronics, you see this concept on the left-hand side here at the bottom under the chip application. You see on the left-hand side of the left-hand side picture is a typical chip application with all the attendant thermal resistances. And then on the right-hand side, if you embed an EHD type system, you see that you have fewer thermal resistances. In other words, you would be able to transfer the heat for a lower temperature drop. That leaves you with higher temperature heat to either reject and take the weight savings as a smaller radiator, or you can take that heat that you're rejecting and perhaps start sort of heat engine if you were to use your imagination or you had such an application for whatever instrument or application you were flying in. How would that look in an electronics chip? That's the picture here on the right-hand side. We actually did put some EHD electrode system in. I believe this is 100 micron channels on the right-hand side of the bottom there. Don't bother with it. This won't work. This was just a proof of fabrication. But we can, in fact, put together a typical electronics chip with an embedded EHD. Next one, Sean. So what are we looking to do? We're trying to get this at least to a TRL-6. We have 3 variable gravity flights under our belt, the latest one being in 2019. And that did, in fact, we can claim, establish thin film boiling feasibility, electrically driven thin film boiling feasibility in microgravity, albeit for 18 seconds at a time, but we did do it 120 times on the variable gravity flight. Then we're using that data and we're moving on to a ISS-based flight where we will have about 60 days of data, at least that's the plan right now, to characterize the heat transfer and the fluid management. The one thing we won't be able to do, of course, is anything above microgravity, but we will be able to talk about the heat transfer enhancement and the capabilities of electrically driven thin film boiling in the absence of gravity, and we will be able to develop design methods for that. It's a microgravity science glove box experiment, and our sponsors are our colleagues down at NASA headquarters, the Biological and Physical Sciences group. And the impact, we hope, then we would be validated for mission and fusion at TRL-6. So you see a picture on the bottom here of the VAMA comet, the variable gravity. That's a zero-G Corp. You know, I got paid to do it. It's a wonderful experience. And then, of course, this is our ISS work. So Sean, the next chart, please. So this is the ISS experiment. What we did do is we demonstrated that electrically driven thin film boiling actually is feasible. We showed enhanced heat transfer up to 2 times what you would get in the lab. And then we normalized the thin film boiling phenomena up to 1.8 G. In other words, we were able to have all the heat transfer data from microgravity, 1 G, and 1.8 G fall on top of each other. And I'll show that chart later. That's significant when it comes to validating technology and design. You don't have to do in situ design. You can design it on the ground, run your experiments on the ground, and have some confidence that you will get the same performance in 0G. Or in this case, up to 1.8 G. And Sean, if we move on to the next chart, I believe that's shows that data. So this is, actually, this is just raw EHD data. I apologize for the background. This is nothing more than applied heat on the y-axis and delta T on the x-axis. So what this chart is to show is that you have the baseline heat transfer, which is the light blue, and that tends to be on the right-hand side. That this is data that we took in the lab. And then what you see is then we have data with the DEP active, and then the EHD active, and then you have, and we show as you activate the EHD components, you move to the left, which means the heat transfer improves as you go along. The big jump you get is with the DEP as opposed to just increasing the flow rate on the liquid pump, the coolant pump. Next chart, Sean, please. This is the data micro G to 1.8, and what you see is, with a couple of exceptions of the baseline data, are some 0G points, which we attributed to sloshing. The variable gravity flight is surprisingly rough, and you will get some fluid sloshing. But what you see is the majority of the data falls on the left-hand side, right on top of each other within the error bars. This suggests that EHD, using both DEP and electrophoretics, or the electrophoretic pump, the coolant pump, you can normalize the heat transfer. And again, I think those of you who are design engineers can see the advantage of that. Next one, Sean. Okay, so this is the microgravity science glove box experiment. The left-hand side is a mock-up of the microgravity science glove box. Our friends at Zen Technologies in Cleveland are the payload integrators, and that is their facility. The right-hand side is a picture of the experiment. We are actually building the engineering module of the experiment as I speak. The rest of the team is off busily doing that while I do the public-facing part of this effort. But anyway, we are in the process of doing that and putting that hardware together, and it looks surprisingly like this picture here on the right-hand side. Next chart, please. So there are commercial applications. There's electronics thermal management, power electronics, wide bandgap communications. We feel that we are able, with enough time and money, to come up with integrated thermal management systems based on the structural thermal plate concepts that we developed with the Air Force a number of years back. The right-hand side picture is certainly my longest professional collaboration. That's Jamal Yagubi, who is currently the department head at the Mechanical Engineering and WPI. And he's doing, this is our first flight on the Vomit Comet probably 8 or 10 years ago. Next slide, please. I think that's it.
Well, once again, I would like to thank our presenters today, Mr. Didion and Mr. Levine, for your time and for sharing your wisdom with us. I think we had a great dialogue today. We learned a lot about the EHD pump and applications for it, and also how to license NASA technology. So thank you everyone for taking the time to be with us today.